In this video, I'd like to discuss what a nucleophile is and what it is that really is the essential quality of a nucleophile and what makes a nucleophile a good nucleophile. And in most organic chemistry courses, what they'll tell you is that a good nucleophile is generally also a good base. So they'll say, here are the good bases, and these are generally good nucleophiles. And although there's some overlap, it's not really the best way to understand what a nucleophile is. It's just the kind of thing they offer students so that they can memorize something and it'll be meaningful. Or maybe it won't be meaningful, it'll be useful, come exam time. And I guess the place to start is by differentiating what a base and a nucleophile is, because this is something that very few students really ever understand. So the first thing is, let's talk about what a base is. A base is just this. So we'll go B with an anion, and we'll have HA. This is our acid. This is usually an equilibrium if we're talking about a weak acid or a weak base. And what we end up with is this. And the basicity of something is a thermodynamic property. So basicity is thermodynamic. What do I mean by that? Thermodynamic refers to the position in an equilibrium. So how basic something is when we say pKa or pKb, well, the essential feature of this is K, which is an equilibrium constant. So how basic something is, what it means is where it sits in an equilibrium. And a nucleophile is a little bit different. So a nucleophile, and actually let's show a leaving group, why not? We'll get rid of that positive charge. Didn't really make sense in this context. And we'll put a delta positive. So we have this. This is a kinetic property. And this is the fundamental difference between a base and a nucleophile. It really doesn't have anything to do with where something sits in an equilibrium. It has nothing to do with K. So nucleophilicity is a kinetic property. So what's the best way to understand that? The best way to understand that is that a good nucleophile, let's actually draw that properly. A good nucleophile has an electron cloud which is polarizable. What does that mean? Well, it means that the electron cloud isn't really tightly held around the nucleus like sort of a hard ball, but is rather much more diffuse, and it's not quite as tightly held by the positive charge in the nucleus. And what that means is that the nucleophile is basically able to sort of polarize itself, something like this. Maybe it sort of polarizes itself this way a little bit, or maybe it can polarize itself a little bit this way. And what that means is that the electron cloud, so to speak, it's more polarizable, and therefore it's more available for an attack. And this is absolutely not a thermodynamic property. This is very much just a kinetic property. And so a good nucleophile is generally going to be something with a large electron cloud. And so if we look at periodic properties on the table, let's imagine we have, let's say oxygen and sulfur. Here's a good example. And actually the one next to it is a pretty good example too. Nitrogen and phosphorus. And we can actually extend this, and why don't we? Fluorine, chlorine. The halogen's actually probably a pretty good group to consider. Bromine and iodine. Nucleophilicity increases as we go down a group. So the nucleophile, the strength of a nucleophile increases as we go down a group. Why? Because the electron clouds in the atom get bigger and they get more polarizable, and that electron cloud becomes more kinetically able to polarize itself and attack an electrophile. Right? They're not as tightly held. If you have something like F minus, Well, the fluorine is extremely electronegative, as you know, and so what that really translates to is it translates into a very hard, tightly held electron cloud. It's not very polarizable. It can't sort of kinetically meet the challenge of attacking an electrophile as easily. Whereas if you have I minus, well, now we have this enormous electron cloud. It's just this enormous electron cloud because it's a very big atom, and the electron cloud is due to shielding. The outer electrons are far more shielded from the protons because there's so many layers of electrons that the electron cloud just ends up being far more polarizable, and you get that kinetic quality that's necessary for something to work as a nucleophile. So sulfur is going to be a better nucleophile basically than oxygen in virtually all cases. Not in all cases, but generally speaking, ceteris paribus, all things held equal. Phosphorus will be a better nucleophile than nitrogen, and of course we can rate the halogens I got that backwards. We can rate the halogens like this. This will be the best nucleophile, then this, and finally this. The one last thing to mention when it comes to nucleophilicity is that resonance has a strong impact on something's nucleophilicity. So if we have something like this, let's say, an acetate anion as a nucleophile, we can expect that this is probably not going to be the greatest nucleophile when it comes to attacking an electrophile. And the reason being that the anion is participating in resonance with the neighboring carbonyl group. So when we can show resonance like this, then what it means is that the electron cloud, so to speak, around the anion is sort of delocalized within the molecule, and it's therefore kinetically not as available as it might be if resonance wasn't a factor. So in this case, that O minus is actually being delocalized over the entire acetate group, and so the electron cloud is simply therefore less available to attack an electrophile. So, in fact, an acetate is generally not considered a very good nucleophile at all. However, if you change it to something like this, if you get rid of that group in which the O minus can participate in resonance, now the story changes. This is a much better nucleophile. So resonance is an important consideration in all things, and nucleophilicity is no different.